Lesson 12 is key features from tables of cubic functions. So in lesson 11, we were looking at like the graphs to find the key features. Here we're just going to be looking at the tables, and then in 12.2, we're going to be just graphing from the tables. So example 1, identify key features from the tables of cubic functions. Key features like intercepts, end behavior, and then relative max and min. So for any function in general, it doesn't have to be a cubic function. The y-intercept is always going to have an x-coordinate of 0. So think like 0, y. The reason is because, if I have a graph and I have a point that is on the y-axis, it's on the y-axis because x is 0. It's not going left or right at all. It'll just go up or down to whatever the y value is. So to find the y-intercept from the table, you look for a point that has an x coordinate of 0. So we have one at 0, 8. And like I said, that's true for any function. It doesn't have to be a cubic function. And then we can use that similar thought process for the x-coordinate, or x-intercept, excuse me. So if we picture an x-intercept, it's an x-intercept because it has a y-coordinate of 0, because it's not going up or down at all from the x-axis. So we can say like x, 0. So to find any x-intercepts, you would look for what point on the table has a f of x or y coordinate of 0. So wherever we have a 0 on the right side of the table. There could be more than one for x-intercept. There's only ever going to be one for a y-intercept. So once you find one for y-intercept, you're good. But for x-intercept, you always want to check for multiple. So we just have one on this table. It's at -2, 0. And then we can move down to end behavior. So but for end behavior, we know, like looking at a graph, is the function or is the graph finishing up or down? We have to approach it a little bit differently on a table. So right here, it's as x approaches -infinity. So that's as the x values are getting smaller. So I'm going to kind of write the end behavior around the table. So if I look at the table, the x values are getting smaller as the table goes up, right? It goes from like -1 to -2 to -3 to -4. So that's x approaching -infinity, and then I just want to see what the other side of the table is doing at that time. So the other side of the table is f of x, and it's also decreasing. It's going from 0 to -8 to -1 to -8. So that would mean that f of x is approaching -infinity also because it's getting smaller. So for the first line of end behavior, as x approaches -infinity, f of x approaches -infinity also, because the x values are getting smaller, and so are the f of x values or the y values. And then for the other part of the table, or not the other part of the table, but the other part of the end behavior, as x approaches infinity, so that means like as the x values are getting bigger, so you have to go down the table for the x values to get bigger. So this would be the x approaching infinity, and then you look at what is f of x doing on the other side of the table. So on the other side of the table, those values are getting bigger. Also, they're going from 8 to 27 to 64 to 125. So that would mean that f of x, since it's getting bigger, is approaching positive infinity. So f of x approaches infinity there as well. And then just if you're dealing with a cubic function, we talked about it in lesson 11, how they should finish going in different directions always for a cubic. So just check that these are different. One should be positive, one should be negative. And then for the relative max or min, you're looking at the right side of the table, and you want to see if there's any points that are like above the points around it, or sorry, any like values that are higher than the points around it or lower than the points around it, or the values around it. So if we look at our table, it goes -8, -1, 0, 1, 8, 27, 64, 125. So it's continuously increasing. So there's no numbers that are higher than the points around it or lower than the numbers around it. So that's not a great example for max or min, but hopefully it'll make a little bit more sense after example 2, where we'll have like a true example. So for this one, we would just put none and then none, because this table is just like steady increasing. It's not changing direction at all. Just all along the right side of the table, it's just continuously going up. And then for example 2, same key features, intercepts, and behavior, relative max or min. So for the y-intercept, remember that's anything that has an x-coordinate of 0, so 0, y. So we have one of those right here. So we have an x-intercept as 0, 2, and then y-intercept, I think I just mixed up my letters. We have a y-intercept at 0, 2, because there's an x-coordinate of 0 there. I always mix them up because you have to have like the x-coordinate 0 for the y, and then, so I always misspeak. But anyways, for the x-intercepts now, we have to have a y-coordinate of 0. So we think of it like x, comma 0. So we'll look on our table, see if there's any points that have a y-coordinate of 0. We have one right here, and then you just always want to check to see if there's more than one. We have another one right here. So those are both x-intercepts because they have that y value of 0. So negative 1, 0, and 2, 0. Okay, and it just kind of goes back to what we talked about up here. Like, in order for it to be on the y-axis, it's because it didn't go left or right at all. So it would have an x-coordinate of 0, or in order for it to be on the x-axis, it's because it doesn't go up or down at all, so it'd have a y-coordinate of 0. And then now we're ready for end behavior, so I'm going to treat it just like I did example 1. So as x approaches negative infinity, that's where the x value is getting smaller, so that happens on the left column going upward. That's when the x values are getting smaller. So it would be x approaching negative infinity. And then we just have to look at what is f of x doing, like on that same part of the table. So on the other side, it's going upward. Like the f of, yes, it's going upward. But as we go up on the table, the values are getting bigger. So that would be f of x, because the values are getting bigger, they're increasing, f of x goes to positive infinity. So as x approaches negative infinity, f of x approaches positive infinity, because the x values are getting smaller here, but the f of x values are getting bigger when we look at like kind of the same set of numbers. And then for the second line of end behavior, as x approaches infinity, that means the x values are getting bigger. So that happens as we go down the table. So this would be x approaches infinity. What's happening on the other side of the table with f of x? Those numbers are getting smaller. They're going from 4 to 0 to negative 16 to negative 50. So that would be f of x approaches, since they're getting smaller, it would be approaching negative infinity. So f of x approaches negative infinity. And then for relative min or relative max, we have to look at like what are the changes of directions on the right side of the table. So we go from 54 down to 20, down to 4, down to 0, up to 2. Sorry, I don't know why I had to say it like that. And then up to 4, down to 0, and so on. So we're looking at, where is it changing direction? There's something funky happening like right around this region. So I would say, let's see, I'm going to read through it one more time. So 0, 2, 4, down to 0. So this is a high point right here. That's where it's starting to change direction. And then for a low point, actually I'm going to finish the high point. So first, sorry, I was getting ahead of myself. So we're going from 4 down to 0, up to 2, up to 4, back down to 0. So this is a point where it's changing direction. It goes from 2 to 4 to 0. So picture like if we're going 2, 4, and then down to 0, that's going to be a maximum. So we would have a maximum at 4. I'm going to go through the minimum, and then I'm probably going to explain it one more time because I know these are like not the easiest thing in the world to like visualize. So for minimum, we're going from 54 to 20 to 4 to 0, and then it goes up to 2. So, I didn't mean to put that on the 4. So that 0 is a low point because it's going like from 4 down, and then it flips back up. So that 0 is a minimum. And then one more time just to explain it a little bit more fluidly. So this section right here, I'm going to pull out a couple numbers. So we're going from 20 down to 4, down to 0. But after 0, we flip back up to 2. So if we really just look at these, going from 4 down to 0, down up, back up to 2. So that 0 is the point where it's flipping and it's going back up. We're starting at a high number in 4, going down to a low number and back up. So that's like our bottom of the well type of situation. So that's why it was a relative minimum. And then for the maximum of 4, we're going to look at these numbers. So we're going from 2 to 4 to 0. So we're climbing to 4. And then after we hit 4, we're going back down. So think like we're climbing to 4. Say this is 4. Then we go back down after. That's a maximum. It's like the top of a peak. Okay, I'll do my best in class 2 to explain that more and kind of give more visuals because I know that these can be pretty tricky. Okay, so for all cubic functions with real zeros, this is just kind of like a general, like helps you check your work kind of thing. So for the first one, so if a function has one x-intercept, like this has one x-intercept, it does not have any relative minima or maxima. Those are just like plural for minimum or maximum. So it's just kind of like if you see something, if you see a graph, you only have one x-intercept, don't stress about trying to find the max or the min. It doesn't have one. So one x-intercept does not have any. That's kind of like we didn't look at it in here, but we looked at a graph just like this in lesson 11, and there were no max or min because it wasn't changing direction at all. It just like gets really neutral through the middle. And then for the second one, if the function, sorry, I don't know why that was bolded, if the function has two x-intercepts, then there's one relative minimum and one relative maximum. So you can see like right here, we have two x-intercepts, and then we have a relative minimum right here where it changes direction, and then right here as well. And then for the last one, if the function has three x-intercepts, it has one relative min and one relative max. So same thing. So I don't, all right, let me finish this. Sorry, I was kind of trying to get ahead of myself. So going up to going down right there, so changing direction, going down to going up right there, so changing direction as well. So these are helpful to know to kind of like check yourself in your work, but I would say like if this isn't something that you need to memorize, it's just something that you can kind of reflect back on and kind of eliminate stress, I would say, especially with like the first example where, okay, I only have one x-intercept, I can't find the max or the min, and then you know this and there shouldn't be one, so you're not kind of like running circles. So 12.2 is graphing cubics from tables, and we're not going to take each point from the table and graph them. We're going to focus on just kind of the key features and use that to kind of more sketch the graph. So these two tables are the same tables that we analyzed in 12.1. So I'm not going to take as much time going over each piece. I'm not going to scroll back and forth because I think that's hard to follow on the video, but just know like these are the same tables. Hopefully you have it in your notes and you can kind of reflect back to it that way. So we definitely want to graph any intercepts that we have, so we'll check for those first. So remember, a y-intercept has an x-coordinate of 0, so our like 0, 8 would be a y-intercept. And we can just go ahead and graph that right now. So 0, 8 is right here. And then x-intercepts have a y value of 0, so -2, 0. So this would be our x-intercept, and then you always want to check for more than 1, but we only have that 1, and then we can go ahead and graph that also. -2, 0. And then we want to know the end behavior as well. It just helps us draw the way that the graph is supposed to finish. So I'm going to kind of talk about end behavior the same way, like on the side of the table. So this is like as we look at the left side of the table and we go upward, the x values are getting smaller. So that's x approaching -infinity because the x values are getting smaller. So at the same time on the other side of the table, the y values or f of x values, those are also getting smaller. They're going from 0 to -1 to -8. So if those are getting smaller, that means that f of x is approaching -infinity. And then on the other like kind of half of the table, the lower half, so if we look at the x column, when it's going downward, it's getting bigger. So that would mean that x is approaching positive infinity if they're getting bigger. And then on the other side of the table at the same time, the y values or the f of x values are also getting bigger. They're going from 0 to 27 to 64. So that would mean that f of x is approaching positive infinity as well because it's getting bigger. And then how that comes into play when we're trying to draw our graph is, so x approaching negative infinity, that means left. F of x approaching negative infinity, that means down. So the graph is going to finish down into the left, and then, oops, sorry. On the other side, the bottom half of the table, x approaching infinity, that means right. F of x approaching infinity, that means up. So right side is going to go up. And that kind of aligns with what we know about cubic functions, that they should be finishing going in a different direction. And then we just have the one x-intercept. So this is kind of, I would picture the main thing that this information up here comes in handy. So if the function has one x-intercept, this like far left one, it doesn't have any relative max or min. So we don't have to worry about drawing those change of direction points. The main thing that comes in handy with this graph, or with when we're drawing it, is just knowing the general shape. How, kind of up here, like there's this general shape where it flattens out in the middle as opposed to like going straight through. There is definitely some curve to it, and the purpose of the section is just to familiarize ourselves with the shape of the graph, knowing that, okay, there's probably going to be like some sort of curve through here, like an inflection point, and then it's going to finish up, and that was a little bit too far up, up into the, I'm very bad at drawing these, up into the right, and then down into the left. Okay, so I know like this is not a very satisfying way to draw these. There's sometimes like sketches that aren't super accurate, but the more important thing to pull from this section is, okay, can I identify the key points? Can I figure out what the end behavior is? And can I draw something that looks like the graph, like a sketch of the graph? So picture like a doodle version of the graph as opposed to putting the exact points on the x and y axis. Okay, so something like this, totally fine as far as a sketch. And then for example 2, same thing. This is the same table from example 2 and 12.1, so like the first half of these notes. So we'll go through it the same way, figure out x and y intercepts and end behavior and so on. So we have a y-intercept right here because the x-coordinate is 0, so this is a y-intercept. I'm just going to go ahead and put that on the graph right away. So 0, 2. And then x-intercepts are when the y-coordinate is 0, so this is 0, negative 1, 0 is an x-intercept. So negative 1, 0 is right here. And then another one at 2, 0 is another x-intercept. And just remember, you can always have more than one x-intercept. You can only have one y, though. Okay, so now we'll figure out end behavior. So on the left, like upper left of the table, as we're going upward, the x values are getting smaller. So x is approaching negative infinity. And then on the same side, or the not same side, at the same like part of the table, but on the opposite side, the right side, the f of x, or like the y values, are getting bigger because they're going from 0 to 4 to 20. So that would mean that f of x is approaching positive infinity because they're getting bigger. And then the lower left of the table, where the x values are getting larger, that would be x is approaching positive infinity because the x values are getting bigger. And then on the opposite side, all the f of x values are getting smaller. They're going from 4 to 0 to negative 16, so they're trending downward, and that means that f of x is approaching negative infinity. So f of x, or sorry, just x approaching infinity, negative infinity right here, that's left. And then f of x approaching infinity, that's up. And then x approaching infinity, that's right. F of x approaching negative infinity, that's down. So this graph is going to finish left and up, and then right and down, and there's going to probably be some changes of direction in between. So we have two x-intercepts. That goes back to this like middle section right here. So there's two x-intercepts, or if it has two x-intercepts, there's going to be one relative minimum and one relative maximum. We already found those for that table. I'm going to go through them one more time because it's kind of a confusing thing, so why not get another like explanation of it? So on this portion, we're always, for max and min, we're always looking at just the f of x values. We're just being at the right column from the table. So we're going from 20 to 4 down to 0 up to 2. So really specifically, like this section right here, we go from 4 and then we go down to 0 and then we go back up. So we hit a low point at 0. This would be a minimum. And then we go from 0 to 2 to 4 down to 0. So really specifically looking at this section, we go from 2 up to 4, and then we flip back down to 0. So that 4 is a high point, it would be a maximum. So since we have those max and mins, that 1, 4, like the max, that's an important thing to have on our graph. So we should add that point also. So at 1, 4. And that's going to be a high point, and that just helps us decide where to change direction. So these are the only points we know really, and that's like okay, it's totally okay. I would maybe, if you can, if you're drawing it, like put the max or the min in a different color, or like highlight them so that you can see where it changes direction. So we had a minimum at -1, 0, so that's right here. So it's gonna change direction there. And then we have a maximum at 1, 4, so it's gonna change direction there also. So it's gonna be like, this would be above the points, this would be below the points around it. Okay, so I'm not gonna get too caught up in like how drawing the curve correctly, how this one, like, we kind of flattened out through the middle. I just really want the end behavior and the key points to be there. So we know it's gonna finish up into the left. So from my far most left, it's supposed to change direction here. So it's gonna shoot upward. Again, probably not super accurate, but we're focusing on the key points and the end behavior. And then bounces off that point at -1, 0. It's going to go through the y-intercept because we know that's an exact point. And then it's going to go up to the maximum, which is 1, 4, and then it's going to bounce off it because that's a change of direction. And then it's going to shoot back down like to the other x-intercept to make sure we cross through that, and then continue down that way. So again, like, it's kind of ugly, it's kind of unsatisfying to graph it, but the main thing is key points are there and behavior is correct. So this is fine in my book. If yours looks like this, that's okay too.